Thank you, Jeff. I'm going to give a brief introduction and then turn it over to Tony to give you some more of the background on shale development and the engineering in general, and then I'll come back and talk through the final nuts and bolts of our material. We've planned this to be about a 45-minute talk so that we'll have time for questions at the end, and we do ask that you hold off till then. By way of general introduction, this shows what the Department of Energy thinks the past has been over the last couple of decades for natural gas in the United States and what they project into the future. So you can see the traditional forms of natural gas here, non-associated gas, have been diminishing over time. Unconventional gas, tight gas, and shale gas have been increasing. So as of a year or so ago, shale gas was making up about 14% of the U.S. natural gas production. The Department of Energy predicts that it'll be 45% of gas production by 2035. Now that's proceeding without a huge understanding of what the environmental consequences are. We're going to talk today just about the greenhouse gas emissions and the greenhouse gas footprint of this technology. I'm sure you've all seen statements like this. From a standpoint of global warming, this is a clean fuel, goes the statement, with 60% fewer emissions than coal. The particular statement I have here is made by a vice president from ExxonMobil back in the fall, but the 60 Minutes did almost exactly the same thing last fall. A lot of people have said this. Is that true? How much do we know about that? Now there's some cautionary notes along the way. This is a letter that the Council of Scientific Society president sent to President Obama and senior administration officials last May. Council's an umbrella group representing about 150 science disciplines in the United States, 1.4 million scientists altogether represented by this. And the council wrote to the president that climate change is an imminent problem. The nation should be working more aggressively than we are on it, but that some of the solutions which are being proposed may be worse than the actual problem. Making ethanol from corn was singled out in the letter as one example of that. The second example highlighted was shale gas, with the thought that this may actually be worse for global warming than simply using other fossil fuels. This is our conclusion slide. Putting up now just to show you where we're going to be going. Most of the talk will be deriving the numbers behind this, but the take-home message of our study is that if you do an integration of 20 years following the development of the gas, that shale gas is worse than conventional gas and is in fact worse than coal and is worse than oil. If you integrate it out 100 years into the future, our take-home message is shale gas is still worse than conventional gas, about the same as coal. With that, I'll turn over to Tony for some more background on the technology. Want the pointer here?
Yeah, thanks, Bob.
Good afternoon. So this is as Bob said, the conclusion slide, but to get to the conclusions, you've got to do a lot of work. And so my job is to prepare you to understand some of the work that we've done in a short period of a lecture. We obviously can't cover all the details, so we will have a paper that will appear. Bob will talk about that later, and that paper will be backed up by online materials and an in-depth engineering report. So what you don't get out of this presentation, you will soon be able to get out of reading materials. Again, before I continue, I would point out that not only is Rene going to answer all our questions, but she did most of the work that I'm going to report on. I would also like to point out that what you're seeing here is exactly what the ACSF has in mind about intercollegiate collaboration. Clearly, I don't know anything about climate science. Bob doesn't know anything about hydraulic fracturing, well design, or pipelines. But together, we're able to put something like this together for you to contemplate. So let me tell you what I'm going to do here. Before we could arrive at a bar chart like this, which you're going to get to see again and again as the talk goes on, and you'll be able to understand it by the time the talk is over, a lot of dog work has to be done all the way back to where the first molecule of methane comes from. So that's where I come in, because my area of expertise is in hydraulic fracturing, rock mechanics, well development, and pipelines. That's been 25 years of my research career. So, as you probably gathered already from that chart, this is not just about unconventional gas, it's about gas. And what you'll find out is that there's a high likelihood, certainly not scientific proof yet, that whether it's unconventional gas or conventional gas, the entire global footprint greenhouse gas footprint has not yet been assessed well. But we are highlighting unconventional gas because it's a contemporary problem for us in upstate New York. And I want to point out that there is a big difference between developing gas from an unconventional well and a conventional well, for the mere reason that unconventional wells are bigger in many senses of the word. So the next couple of slides, I will highlight how that biggerness impacts the numbers that we're going to show you between unconventional gas and conventional gas. So a unconventional well has a longer total length. It may be just as deep, but because to get unconventional gas out of shale, economically, one has to have long laterals. The laterals can be, in fact, longer than the depth of the well. You have more and heavier drilling equipment. There's a longer drilling time, there's a higher probability of drilling problems, and there's more venting during drilling. That is, you're making gas during the drilling process. As you'll probably gather as I proceed here, there are a lot of technical details involved in developing any gas well that the public doesn't know about. You're going to learn about a couple of them today. Bigger also means that the frac design and the number of stages is bigger. There are more and heavier fracking equipment required. There are more stages and total volume per stage. And there are more plugs and longer drill out period. And I recognize I'm already using jargon that some of you aren't familiar with, so it'll become clear in a minute. And finally, because these wells are bigger, there's more flowback waste, more produced water. That's a different issue for a different time, but coming back with the flowback and coming back with the produced water is methane. And so there's a higher volume of methane over a longer period of time coming back during the time when the well is not yet producing gas. It's still producing waste. And finally, during that period of time, there's more venting and or flaring of the gas, which is waste of gas. So, typical conventional well, you've all seen this diagram many, many times, goes straight down into a gas deposit, a gas resource. That's a lot different than an unconventional well, where you might go down the same or shower depth, but you're going out, typically nowadays on the order of a mile in Pennsylvania and other shale fields around the country and around the world, up to 2 miles. And so this is a bigger enterprise than a conventional well. What do I mean by bigger enterprise? We had to decide in conducting our study what was going to be a representative unconventional well. We wanted to make sure that that well was not an extreme case, too small, biggest ever. We wanted to make sure it was representative of Marcellus Shale. And so I wanted to point out what things are happening around the world, which we think ultimately will be coming to Marcellus, but are not yet here. And we did not use a well pad of this design in our study. This is the second largest frac job ever done in the world. As you can see, it's not your grandmother's conventional well in upstate New York. This is currently the largest frac job ever done. There are 16 wells from this one pad, 417 million gallons of water. You can read it all, but the point here is that these things require more CO2. They produce more CO2 because of what we call indirect emissions from all the equipment that has to be run to develop the well, and they produce more fugitive methane. 500 frac stages, that's 500 plugs that have to be drilled out or removed. 10,000 foot laterals means that there's a heck of a lot of more flowback coming from this than from a conventional well. 40,000 horsepower pumps running, in this case, for over a year continuously, consumes a lot of fuel and produces a lot of CO2. So, but these are not the wells that we focused on. We decided to be conservative. And as you'll sense from everything we talked about, we've tried to be conservative all along. We're not trying to be hyperbolic in our statements. So this is the typical well, the generic well on which we based our numbers. It's typical of what Chesapeake has done. In fact, it's the average Chesapeake well in Pennsylvania. And I don't expect you to be able to read all the numbers I'm going to show you in the spreadsheets you're going to see in the next few slides. They're here to show you that we've done due diligence. And it took a lot of work on Rene's part and my part to dig up these numbers, and they're all industry numbers. They're not academic pie in the sky. For example, if we know a typical well in Pennsylvania, we can back figure things like how much equipment does it take to drill that well and to produce from it. Another spreadsheet that you'll see in the materials that we'll produce online and in a report breaks down all the combustion equipment at the well site. All of this is producing CO2 24/7 for as long as all the wells on that pad are going into development. So again, to emphasize the point that an unconventional well is not a conventional well, just to point out again, it takes 10,000 horsepower more or less, to do a hydraulic fracturing job on an unconventional well. All right, let me highlight this business of methane, natural gas, that comes out of the well and does not go into the pipeline. Okay. There are three sources of that gas during conventional drilling and unconventional drilling, but more so in unconventional drilling for the reasons I just pointed out. During the drilling process, long before any fracking occurs, as you heard from our seminar last week, it is highly likely in the Marcellus Shale to encounter shallow gas. While you're drilling through that shallow gas, it doesn't stay down there, it wants to come up the well, and it does, and it's vented. It's not flared, it's vented. It's exhausted to the atmosphere. During flowback, after each stage of fracking, and there are multiple stages of fracking, production is not yet possible, so the gas that comes up during flowback is either vented or flared. And I should point out that there are many countries around the world where flaring is illegal. It is legal in New York State and Pennsylvania. During plug drill out, again, the well cannot yet go into production. They have to remove the plugs between each stage. During that time, there's gas flowing up the well. That gas is either vented or flared. We conservatively assume in our numbers 50% of the gas that comes up during these periods is vented and 50% is flared. During drilling, as I pointed out, whether it's a conventional well or a non-conventional well, there is typically encountered in these regions shallow gas. That shallow gas goes up the casing and it's vented to the atmosphere. We do not include those sources in our numbers. Again, we're trying to be conservative. We do not include any accidents, any incidents, any methane migration from around the well, or any methane migration up the well during production, during drilling, or during hydraulic fracturing. So again, we're trying to be conservative. Those are all sources of additional methane. We're ignoring them. Okay, flowback gas. It takes somewhere around 2 weeks to go from we just finished the hydraulic fracturing to connect it to the gathering line, to connect it to the transmission line, to connect it to the distribution line that goes into your gas stove. During that 2 weeks of flowback, the gas that's coming back with the flowback can be a very high volume. It's typically the same volume that you would get on the first day of production, except that it's mixed with a liquid. That gas is either vented or flared. And as I said, we take that into account. It's a very large source of gas. Here's another table that you'll see when you read our stuff where we've gone to a bunch of unconventional sources, gas shales, tight sands, and looks at the amount of flowback gas that's created during the flowback period. As you know, in Pennsylvania, right now you have two choices. You can flow back to an open pit, and during that time, gas is vented, or you can flow back to tanks, steel tanks. Those tanks are also vented. That vented gas is either vented or captured and flared. If it's flared, that's what you see. What you can't hear is 100 dB at a half a mile. If it's vented, it's coming out of vents, or if it's flared, it's coming out of flares. Plugs. What's a plug? Most people don't know that when you're fracturing a long lateral, it has to be done in stages, typically 500 feet per stage. Between each stage, there has to be a plug, either a concrete plug or a mechanical pneumatic plug. After a stage has been fracked, that plug is set. Next stage is fracked. Next stage is fracked. And when all the stages are fracked, those plugs have to be removed. That takes a couple days. And during that period of days, there's gas flowing back that cannot yet be captured. So it's vented or flared. The bottom line here is I skipped a lot of stuff. But what we get to eventually is the ability to characterize for each unit of energy produced by a typical unconventional well, how much CO2 is emitted and how much methane is emitted. And we do that on the basis of upstream, midstream, and downstream calculations. Upstream means everything before the gas gets to the first compressor station. Midstream means from the time it gets to the compressor station to the time it gets to city gate, and downstream means city gate to your house. In all those regions, we had to do calculations of purposely emitted, accidentally emitted, or unknown sources of methane into the atmosphere. So I'm going to conclude there by pointing out, I'm going to hand back to Bob. He's now going to build the bar chart that I started with and he ended with, piece by piece, to show you how we assembled all this data, mostly because of the work that Rene did, so that we could tell the whole story. Bob?
Thank you, Tony. This is the building block of our study, and this is the direct emissions of carbon dioxide at the time a fuel is burned. So for either shale gas or conventional gas, you're getting about 15 grams of carbon as carbon dioxide per megajoule of energy that's available to do work. For coal, the emissions are higher. For diesel oil, it's less than coal, but higher than for gas. These are Department of Energy data. These are pretty well accepted, and these data are the basis of the statement that the emissions from gas are less than from coal. They are for the carbon dioxide of direct combustion. It's only part of the story, though. It's a small part of the story. Now, Tony was talking about the incredible amount of work that Rene and he did to try and look at the indirect emissions, the trucks, the pumps, the compressors, and all. Disappointingly small number when you add it all on.
For the amount of work that
For the amount of work, yeah. It's a very small bar per hour of time invested in it. The red bar are these indirect emissions. They are greater for shale gas than for conventional gas by about 40 or 50%, but it's still a relatively small thing. It's dwarfed by the direct emissions from combustion. It's comparable for coal. It's a little bit larger for diesel oil. We've done this accounting. It's a small part of the story. The big part of the story, and Tony's already talked about this some, is methane. Methane is the real problem with the greenhouse gas footprint of gas in general and shale gas in particular. The natural gas is mostly methane. 90%, 85, 95% of natural gas is methane. Methane is the second most important greenhouse gas after carbon dioxide in current human-induced global warming. And it's a far more potent greenhouse gas per mass or per molecule than is carbon dioxide. So even small leaks make a difference. Now a little bit of background. The Environmental Protection Agency, way back in 1996, worked with industry to come up with a series of emission factors, what the methane leakage rates are from the oil and gas industry. And they produced a big volume, which has essentially been the Bible for people to try and calculate the consequences of that ever since. 1996 was a long time ago, and there's been accruing evidence that the numbers from EPA were low and wrong. EPA was resistant to saying anything publicly about that until November 30th of 2010, a couple of months ago. And on November 30th, EPA issued a new report, this thing, the background technical support document on greenhouse gas emissions from the natural gas industry. And they say that the old 1996 study was done at a time when people really weren't all that concerned about methane, and there wasn't all that much known, and they updated it. They said that the old 1996 document potentially understates. I'm hammering on this because I'm going to come back and talk about it several times over the next half hour. And they give new emission factors, not for all parts of the industry, but for many parts of the industry. And this potentially understated is really an understatement. Because a lot of the emission factors they put out are orders of magnitude larger than in the 1996 study. We had, at the time this came out, we had a draft manuscript already submitted for publication. And a large part of that was a critique of the old 1996 EPA study. This came along and sort of changed our story. We went back. We didn't want to just accept the new EPA story without understanding why they were changing. So we went back and looked at their sources, rethought a lot of our numbers. Rene has worked very, very hard since November 30th. I also just want to point out that at the global level, there's a lot of uncertainty about how much methane is going into the atmosphere, where it's coming from. It's a very poorly known circle. I've worked on methane cycling for 35 years. I served on a National Academy committee as the methane expert back in the 1980s. We didn't understand it then, and we still don't. But there's new science all of the time. I just want to highlight this one. A paper that came out 3 or 4 years ago now. They looked at the radiocarbon dating of methane that's in the atmosphere. And you can determine whether it's recent methane that might come from a wetland or whether it's fossil methane, which would come from fossil fuel source. And the conclusion is that 30% of the global methane in the atmosphere has to come from these fossil sources. That's twice as large as the Intergovernmental Panel on Climate Change had said, or any other inventories. So I'm highlighting just the uncertainty there. Okay, I'm going to run you through some numbers on where methane's coming from. Tony's introduced these. I'm going to give you hardcore numbers now. Methane is vented and leaked during shale gas development at several different stages. We're going to go through each of these, and I'll give you some numbers, and then we'll put it in perspective. This is a similar version to a slide Tony just gave. We're looking at shale gas and tight sand hydrofracking jobs here for 5 places. These are the only places where we've been able to find data. The leads for these we got out of the EPA report, but Rene tracked these down and we independently verified the numbers. Our conclusions are a little bit different than the EPA. I think ours are a little bit stronger, quite frankly, and I think we do a better job of documenting it. This is the amount of methane that's actually emitted during flowback. I'm using metric units because I'm a Earth system scientist, not a civil engineer. We've normalized that to per day here, and I'm comparing it. Tony made the point that the amount of methane that's coming up from these initial flowback waters is pretty much the same as the initial production of the well once it goes online. That's demonstrated here. This is the initial production. So higher producing wells, higher pressure, you get more methane vented to the atmosphere at the time of the flowback time. This is the lifetime production of wells representative of those basins, and so over here we've expressed it as a percentage. 3.2% of the lifetime production of a well in the Haynesville Shale Formation is vented to the atmosphere in the first 12 days of flowback after the hydraulic fracturing. Big number. That's just to point out again that this is basically a free flow of gas, is what it is, at that initial period of time, coming back to the water. You can see some patterning here. We've got the highest percentage leakage in the Haynesville because it has the highest production initially. It's a higher pressure well. We've got the lowest number here in this tight sand formation, which has the shortest flowback. It's a lower pressure well. But how did we use these in the end? Well, I want to emphasize that these are the best available data, and Rene worked incredibly hard at getting these, and we had a lot of help from industry, I will say as well, in interpreting these and getting them. But they're limited data. These are not published data. These are things teased apart out of PowerPoint presentations here and there. And so rather than try to extrapolate based on any complicated formula, we've ended up simply taking the mean of those values, 1.6% leakage. 1.6% of the lifetime production of a well leaks in the initial flowback period. Okay, so I'm going to walk you through a developing table here. The initial drilling and completion, there's not a lot of leakage in conventional gas. We're saying 1.9% of the lifetime production of a shale gas well is leaked during the initial flowback. It's 1.6 with the flowback fluids, another 0.3 during those drill out of the plugs that Tony talked about. We're being very conservative on the 0.3 because it'd be equally easy to argue that it's 0.6 during the drill out. Throughout, we're trying to be conservative. And to reiterate a point Tony made, there's also methane leakage when you drill through some of those shallow formations. We're not including that in our analysis. We know it's happening, but we don't have any way to put a number on it. We don't know if it's a big number or small number, and so we're leaving it out, again, to be conservative. Okay, once a well gets going, it's in production, there's continual leakage at the well site over the life of the well. And we think that's about 0.3 to 1.9% of lifetime production of the well. We think it's the same for conventional gas and shale gas. We see no reason to think that's different. These data are from a General Accountability Office study that came out last year, looking in detail at 4 basins in the American West to try and see if the U.S. taxpayers were inadvertently getting ripped off by industry. That's the basis of the data. The data behind them are industry data and EPA data. So they're their numbers. The 0.3 reflects best technology. The General Accountability Office doesn't think you can do better than that. 1.9 is the high range. They don't give a mean. We're giving a range as well. Another leakage is what we call this venting during liquid unloading. What's liquid unloading? You get fluids in the well, interferes with production of a well. Industry gets rid of that fluid and increases the flow of a well. That's called liquid unloading. It happens periodically. Some wells, you never do it because it's not a liquid problem. So at the low end, there's no venting because there's no liquid unloading. When there is liquid unloading, you can get up to 0.26% of the production leaked. Again, this is from the General Accountability Office using industry data for that. There are leaks during gas processing, and what's gas processing? In some areas, gas comes out of the ground and you can put it right into a pipeline with no processing. That's true in northeastern Pennsylvania in the Marcellus. But in southwestern Pennsylvania, in the Marcellus, it's loaded with hydrogen sulfide and higher molecular weight hydrocarbons. The gas has to be processed before it's put into a pipeline, and there's leakage associated with that. In this case, we're using estimates from a report by Shears et al., 2009. This is American Petroleum Institute study. So these are the industry's estimates of what the problem is. There's no processing, there's no leakage. If there is, they're saying it's close to 0.2% leakage. So we sum those up and get sort of a preliminary look at what's going on. Total leakage during production and processing varies from about 2.2 to 4.3% for shale gas. It's less for conventional gas. And overall, by our analysis, the methane emissions from shale gas are about 80%. If we compare the higher end numbers to about 7-fold, if we look at the low end estimates, greater emissions from shale gas. That's only part of the story because, of course, you got to deliver the gas to consumers where it's going to be used for whatever it's used for. And there's leakage associated with that. So we've come up with an estimate of the leakage during long-distance transmission in pipes, local distributions in pipes, and storage, because you need to store it to deal with seasonal differences in supply and demand and to equalize pressures, etc. And there's leakage associated with this. This is just an illustration of that. A gas storage tank, and the naked eye you don't see anything. If you take a camera that's tuned to the infrared radiation absorbance spectrum of methane, you can see large amounts of methane flowing off to the air there. Another point I want to make is that the gas transmission pipelines in the United States are fairly old. These are the big long-distance things. The local distributions into one's home, etc., are older yet. But if you look at the age of pipelines in terms of cumulative distance here, about half of the long-distance transmission lines in the United States are half a century older or older. Old stuff. So it shouldn't really be a surprise that these things leak. Gases leak. We took two approaches to estimating what the leakage from storage, transmission, and distribution is. The first are direct measurements. There's this paper published in Nature 6 years ago. It's done by scientists at the Max Planck Institute. It's a very nice study. They looked at leakage from the pipelines from Russia, the newer pipelines from Russia, post-Soviet pipelines going into Europe, and direct measurements of leakage together with, they used some numbers from this old 1996 EPA study, which I've already told you is a little suspect. They end up with a number saying 1.4% of the gas you put into a pipeline and storage system leaks to the atmosphere. We think that's low because of their reliance on these EPA numbers, which seem to be low. The other way we looked at this was what's called missing and unaccounted for gas. And this is an accounting scheme. State of Texas has pretty good records on this, and we use the state of Texas data and extrapolated them. So this compares the measured production at a gas well with what is finally sold to consumers. And on average, over the last decade, 3.6% of the gas that's produced in Texas never makes it to consumers. Well, where does that go? It's either vented to the atmosphere or it's stolen. Well, and no one knows which. And industry's arguing about which. They say it's not vented, it's stolen. It could be stolen, I don't know. I will point out that the state of Texas in 2007 had a proposal in their legislature to put a 5% hard cap on pipeline leakage because they viewed this as a problem. Industry lobbied very heavily, saying it would be a huge economic hardship to try and meet a 5% leakage rate from pipelines. Okay? So we think the 3.6% is pretty conservative, but it's larger than the direct measurement. But again, the direct measurement has some extrapolations that are questionable. So we used the range, 1.4 to 3.6% for transmission, storage, and distribution. So you sum up the whole thing, now from the time of developing the gas to final consumer, and we're saying 3.6 to 7.9% of the lifetime production of a well is going to the atmosphere as methane. Somewhat more than conventional gas, but conventional gas isn't very good either. And the difference between these is only in that initial flowback and drilling out procedure. So the shale gas emissions are 30%, to perhaps twofold greater than those from conventional gas. All right, how do our numbers compare with what else is there in the peer-reviewed literature? I will say, I'll cut ahead a little bit. We have a peer-reviewed paper that's been accepted for publication. How do our numbers compare with others? Well, to begin with, there are no other papers on methane emissions from shale gas. There is nothing in the peer-reviewed literature on this, which is why we're using all these PowerPoint talks and things of that sort. Our numbers are comparable to those from the November 30th EPA report. They're not the same because we've tweaked their assumptions a little bit differently. Our numbers are actually a little bit lower than the EPA estimates. And both our numbers and the new EPA numbers, in terms of the initial flowback period, give estimates that are 2 orders of magnitude greater for methane leakage than the old EPA 1996 studies. Now, there are peer-reviewed papers on conventional gas for methane and the greenhouse gas footprint. There are 3 papers in the last 15 years. And so we can compare our numbers with those, our conventional numbers versus their conventional numbers. One of those is this paper by Hayhoe et al., 2002, in Climatic Change. They gave a range of leakage of 0.7% up to 10% and said their best estimate was 3%. Our range is 1.7 to 6% for conventional gas. So we're in the same range they are. Totally different set of assumptions, but same idea. This paper in Nature didn't give an overall life cycle analysis. They just looked at the pipeline storage aspect. They came up again with that 1.4% number. We used that as our low-end estimate, so obviously we're overlapping with them. Our high-end number is higher. Again, we think that they are underestimating it because they're relying in part on the old EPA 1996 study, which has now been superseded. EPA itself says those are not reliable numbers. And the third study is one by Yamarillo et al., published in Environmental Science and Technology 4 years ago. They use a life cycle analysis lifetime rate of 1.1%, lower than ours, but is based entirely on the EPA 1996 report. So we think it's too low. Okay, now how do we take our methane numbers and put it into equivalents of carbon dioxide for global warming? We use this paper, which came out in Science in October 2009, Shindell et al. And they give a global warming potential. Global warming potential is the integrated influence of a gas compared to carbon dioxide on global warming over some defined period of time. And a lot of people think that the global warming potential for methane is 21. You'll hear that all of the time. It's 21. You've got to use 21. 21 is based on the Intergovernmental Panel on Climate Change report from 1995, looking at a 100-year integrated time period. In 2007, the Intergovernmental Panel on Climate Change upped their number for 100 years to 25 from 21. Won't go into exact details why, but they also said, it's important to look at shorter time frames too. And over a 20-year integrated time horizon, methane is 72-fold more potent than carbon dioxide, they say. Why should you need to look at the shorter time horizon? Because we want to be solving climate change now, and we need to worry about those short-term aspects. The Shindell et al. Paper, again came out in Science, gives a 33 factor for the 100-year integration and 105 for 20, higher than the IPCC 2007. That's because they're including indirect effects of methane on aerosol formation in the atmosphere. Now, I'm not an atmospheric chemist, and I wasn't quite sure how much credibility to give this. So I contacted the authors who wrote this section of the IPCC report and asked them, what do you think of this? Should we use these numbers or your numbers? And they all said, oh, you should use these. And the next version of the IPCC, when it comes out, in 2014, is it? They will be using these numbers or some more recent derivation and not these numbers. So we're using these numbers. Why is the difference in time frame? It's because methane doesn't hang in the atmosphere as long as carbon dioxide. Methane's in the atmosphere for about a decade. Carbon dioxide's in the atmosphere for about a century. So in the short time period, right after emission, methane's an incredibly potent greenhouse gas, but over a century, it's gone. And these are integrated time intervals. Okay, so that takes us back to this figure. Here we have for shale gas, we have low and high estimates for methane leakage. This is our low methane leakage rate. That's our high estimate. Same for conventional gas. We have coal that's either surface mine or deep mine, and we have diesel oil. We have methane for all of these. There's more methane leakage from deep mine than for surface coal because of the pressures at depth. But there's a lot more methane leakage from gas, either conventional gas or shale gas. These are all in carbon dioxide equivalents. And this particular slide is showing you the 20-year integration. And Tony kindly added these lines yesterday so you can get your eye. This is our low estimate and our high estimate for the greenhouse gas footprint integrated over the first 20 years after the gas is developed, compared to other things. And shale gas is worse than coal, worse than diesel oil, worse than conventional gas. If you take the longer time frame, again, the methane will be dissipating from the atmosphere, so it's less of an issue, but of course you still have an effect. And so this is our 100-year comparison. And again, Tony kindly drew these lines in for us yesterday. So the low end estimate, integrated over a 100-year time period for shale gas, and the high end. At the low end, shale gas is worse than conventional gas. It's about the same as diesel oil. It's not as bad as coal, although it's not that much better than coal. At our high end estimate, and again, we think we're being pretty conservative in these methane leakage numbers, shale gas is worse than coal. It's worse than anything else. I'll let you ponder that for just a minute. All right, I want to qualify a little bit. We've been working on this for about 15 months or something now, and I've given talks, and Tony's given talks, and there's been a fair amount of attention to some of our work, and I've been accused fairly often of being a pawn of the coal company in this. And there's actually some bloggers who've written that I'm being paid by the coal company to do this. So I wanted to say I've never received a dime from the coal industry in my life. I've never received a dime from the oil companies. I have worked on the environmental consequences of oil pollution and coal, and I think those are terrible technologies. So I'm not saying that those are better than shale gas, but we need to look at the true environmental consequences of shale gas when we do this as well. Now we have a paper. It's in press now in a journal called Climatic Change Letters. It covers everything I just ran through. Tony pointed out that we have a much more detailed technical report, Santoro et al., which we will post online as well. So our current summary is already online. We're going to put all of our references, all the supporting material, and access to this paper as it's published online. The paper is currently scheduled to be published somewhere between April 1st and April 14th next month. So it'll be out soon, and we'll make it available as soon as it is. It's embargoed in the meanwhile. The publisher has ordered us not to publicly share it until it does come out. Just want to acknowledge we have had funding from the Park Foundation for this work, which I appreciate, and even more importantly, we've used the funds that go with my professorship that Mr. Atkinson has endowed to support this and help pay for Rene. We'll end there. Tony, you want to give a concluding thought or two?
Sure. One, we do not intend for you to accept what we reported on today as the definitive scientific study with regards to this question. It's clearly not. We pointed out as many times as we could that we're basing this study on, in some cases, questionable data. What we're hoping to do by this study is to stimulate the science that should have been done before, in my opinion, corporate business plans superseded the national energy strategy.
Thank you.
That's the only comment I have to make.
I agree with that. A lot of the data we used are really low quality, but I'm confident that they are the best available data.
It makes a big impression what you said. My question, though, is if you took an equally careful look at coal and methane from coal and CO2 from coal, would coal come out looking the same as the old EPA estimates, or would coal also look bad?
We didn't look as carefully at coal. I mean, these numbers, these methane numbers are ours, these indirect numbers are ours. The blue across the way here is Department of Energy. The question is, if we looked as carefully, would they go up? I think those are better known numbers than the gas numbers for a variety of reasons, one of which is that methane is regulated in the coal mining industry and it's not in the natural gas industry. the numbers, there is a range of numbers which one could pull out of here. The particular numbers I'm using here for the surface and deep mine coal are the mean values from the IPCC 2007. So they're going into the global inventory from that. They actually are higher than what the EPA 1996 inventory numbers are. We use them again to make the comparison conservative. But we didn't put anywhere near the amount of effort into them, but I'm sure they are lower than the natural gas. And they still aren't great numbers either.
Okay, let's take, what, in the back of the room there?
Yep. Hi, Bob. I have a question regarding a film that I saw a few years back. I believe it was made in '05 by BBC regarding global dimming and some of the effects. I believe it's the aerosols and the effects that coal has on precipitation, I believe. And I think a lot of this came about right after 9/11. In the last, like 3 days afterwards, that they noticed a big jump in the temperature, the global temperature.
Mm-hmm.
Are you familiar with that?
A little bit. Let me just, we've got some backup slides here, depending on what kind of questions we get. Let me show you this one, which is from the IPCC. And this is just what the IPCC, as of 2007, was saying in terms of relative atmospheric forcing function. So there's a number this way means it causes global warming. A number this way is global cooling. And the sum total is just the sum of those.
The
That sort
aerosols
of,
have a negative effect.
yeah, the aerosols have a negative effect. They are global cooling agents
More
because
reflecting,
they increase the albedo, the reflectance of the Earth. Methane interacts. This is the story behind that Schindel paper that came out a year and a half ago now. Methane interacts with the aerosols because it affects the rate at which aerosols are formed in the atmosphere. You put more methane in, you get less aerosol formation. So that's the interaction
We
there.
have three right here in the middle of the room, so let's start with you and then we'll go across.
I don't know if this is for Bob or Tony.
But it's for Rene.
I noticed, Rene, I noticed that you're using along the way in the calculations the percentage of lifetime production rather than a sort of a unit number. We've discovered that annual production figures are self-reported and by the industry and not verified. Nobody goes out and checks those meters, which obviously has the potential to shortchange both the royalty received from the property owner, the local tax base, because it affects property taxes, and the corporate taxes if it's underreported. But for your purposes, if there's a change, if the annual production numbers aren't accurate, or then the lifetime production numbers aren't accurate, then that could change your percentages. Does that affect your analysis if it's seriously underreported?
Let Tony address the question of how far off our numbers might be. But let me show you where it comes in here. It shouldn't affect any of these, but it will affect the top line there. So when we're using the production numbers there, it will affect that number if we're off.
Yes.
Okay.
And the only honest thing we could do, again, with the data that we have available, is to use industry data. So we used the Chesapeake standard decline curve for the standard Chesapeake well in the Marcellus to estimate estimated ultimate recovery. It's an industry number.
And we did check those numbers against the reported numbers because there's I forget the author who's been saying that the productions are overestimated, that industry is inflating its potential production. I did go through the calculations.
For the Marcellus.
Well, we don't have data for the Marcellus emissions, though, right?
No, we
But
don't.
the production data
Production data we
verified
do,
by
right.
the decline curves.
Right. You were basing that on other.
Yeah, it's based on those 5 other basins we showed you. Two of which are shales and 3 of which are tight sands.
So the numerator and denominator could change with more data.
That's right. That's
what
the
I
point.
think Tony's
Absolutely.
point.
That's the point.
Right.
And let me just as an aside say that, again, the quality of the data behind that number are pretty lousy. They're these
That's what they're saying.
weird PowerPoint sort of things. I think we're to do it, and Tony and Rene and I have been talking with Jed Sparks and with others. We want to mount a field campaign and go out in the Marcellus Shale and do micrometeorological fluxes of methane at a time of venting and get a real number on this, which has never been done.
Right.
We're optimistic we can get funding and do that over the next year.
Okay. Larry?
I'd like to return to Rick's point. In the Hayhoe paper that you cite, as I read her table, she reports a number for the amount of methane that's released in coal mining. We all know about the canary in the coal mine and about the methane explosions in coal mines. There's a lot of methane that's released, and her number, if translated and put on the same basis as your numbers here that you have in your figure, would add 41 grams of carbon per megajoule of energy from the coal. In your figure there for the surface mining, for the deep mining, you have 5. So that's quite a big difference.
Her numbers are just for the deep mine, I believe. Her surface numbers were
nonetheless,
lower than this, in fact.
Well,
And her surface number was indeed higher, as you say. The IPCC has about 3 or 4 paragraphs saying why they think that's an error, and I think it was a calculation misreport.
well, it makes a huge difference.
I agree it does.
Yeah.
It completely changes your revision of the greenhouse impact of the
Relative to deep mine coal, it won't change the surface mine coal.
No, I'll have to look at it carefully.
There's
should.
just,
Okay, let's keep going. So you have one, Larry? And then we'll go back. I'll come back to you.
Just a quick question from an engineering point of view. It seems like a large fraction of the excess methane production is associated with the development phase and the flowback water. From an engineering point of view, is that a problem that can be engineered out of the system or reduced?
Excellent question. So there have been, over the last decade or so, large international conferences held by the gas industry on the topic of flaring and venting. I mentioned that in many countries it is illegal to flare for obvious reasons. That you're wasting somebody's gas and you are doing something not necessarily good for the atmosphere. So these conferences highlight on exactly the question you're pointing out. Are there technologies available that we can recover gas coming up the hole earlier in the life of the well so that there's minimal venting or flaring or a total elimination of it? Yes. And just like everything else in the industry, these technologies are just now coming around, and they're extremely expensive. And a company, you can finish the rest of the story.
Sure. But I mean, it's an issue
Yes,
to
the
come
answer
back
is
to
yes.
later.
The answer is yes.
Yeah.
Because I think you're missing an important part of the picture. And it seems like maybe you need a mechanical engineer or electrical engineer to...
our civil engineer is not good enough?
I am also a mechanical engineer, Bill. So tell me what I missed.
Okay, tell me what you think. Because I think you've made a mistake because you're presenting grams of carbon per megajoule of heat. And the goal here is to produce electricity.
Yeah. Well, certainly
So
electricity
you
is
should be presenting
one end
grams of
state,
carbon
right?
per megajoule of electricity.
Right. You get a different.
Now, if you assume 30% efficiency for converting coal to electricity versus 57% efficiency for converting gas to electricity.
Milt, we didn't make a mistake. We just didn't get around to talking about it yet. But thank you for raising
It's actually
the issue.
it's in our paper. I didn't show
Presumably
it
it would
in
be
today's
in the
talk.
paper, for sure.
You know,
It is. Although, let me
so then
just.
it's a completely different conclusion that I would draw using your numbers. In
Well,
terms of, it's not worse.
we
Right.
deliberately.
However, in fairness, though, we use a lot of gas right now to heat homes and to provide hot water.
Well, but we're
That's
talking
not going
about
to go
using-
away.
We're
right?
talking about
Right.
replacing coal with gas.
And we're talking
Well,
about using it
and
for
that's-
transportation
Right.
fuel and
For
replacing oil.
Right.
Well, that's for electricity. Most coal is used for electricity.
These numbers are per megajoule
Right,
of heat
right.
generated
For the
to
coal.
allow useful work.
But not oil. Right.
You can use it for electricity, and you're correct, although I think 57 versus 30 is a high-low estimate. Coal could be used at 45, and the mean
Well,
for
the mean is in the mid-30s for coal.
It's actually lower than
Right.
30.
four plants built in the 1950s.
Well, for the average for the country, which is what we're looking at here.
Which are from the 1950s.
Well,
But yeah.
but we have to take an
Okay.
average.
But yes,
Yeah.
so that's a factor of about 2, and you can,
What does that say to your chart?
well, it would
On electricity.
it would increase those relative to this by about a third. It's still, natural gas is still worse. It's in our paper.
No, no, it's not.
It's not.
No, it actually is.
If you
You
take
haven't read our paper.
Jeff, the purpose of this seminar is not to have an open debate.
Right, I think once
the
we
purpose
see it,
is,
right, it sounds like
the
you
purpose is
covered
to
it in the
stimulate
paper.
further study.
Right, right.
And we purposely didn't focus just on electricity because electricity is
Use
not
gas
the
for
only
other
use.
things, yeah.
If you look down the line after carbon dioxide and methane, what are the next criminals? Are they? They play into this.
Nitrous oxide would be the next most important greenhouse gas, and we have estimates for it. We didn't put them in here. It's pretty small relative to this.
This is greenhouse warming though, but there are
Yeah.
other category
Sure.
emissions which are equally
Oh, absolutely. No, it's just
SOx, NOx,
absolutely.
particulates.
And and coal is far worse for a lot of those things.
Sure.
If you care about mercury, for instance, coal is terrible. Natural gas is great. So again, we're focusing here on the greenhouse gas aspects.
We got the cameraman has a question.
Yeah, and
That's got to be a first, right?
I don't think so. When we're dealing with the integration of carbon dioxide equivalent of methane, what I don't really understand is if they keep doing production, why does it diminish? For 100 versus...
This is from the time it's emitted to the atmosphere.
That's about the decline curves, and I think you referred to probably Arthur Berman's work challenging that. Okay, so I didn't quite understand your response, because it seems to me like, none of these wells using hydrofracking processes have gone through their full life cycles. They've gone through maybe economic life cycles, but not their full production cycles.
Barnett wells, some Barnett wells have.
Okay, so the question is, like Barnett is an industry insider critic, and maybe you can answer this too, is really saying that they are in fact vastly overestimating the production. And they're speaking primarily to stockholders rather than, from a scientific perspective about it. So I'm just kind of wondering how, from your perspective, how much uncertainty you think there is in the estimated ultimate recoveries from the wells, and how that would affect, how sensitive your results are to those estimates.
You can point.
Which one do you want?
It affects that number.
Right.
Very sensitive to that number. Because the reason
That's a
why
high
that number is
limit,
up there is
right.
because we're multiplying the estimate of the ultimate recovery of a well by an industry standard. Here's the percent that we lose during flowback. So if you have less, less EUR, that number comes down.
Declines in the first few years, so you're getting most of the gas out in the first 1 to 5 years, certainly. So.
If they're over-reporting production, then this would be worse. If they are underestimating it, it would be better. But there's a huge amount of uncertainty, quite aside from that number. There's not a lot of data behind that number.
Yeah. So you point out, on the one hand, they want to report one thing to the shareholders, and they want to report something else to the EPA. It's a rock and a hard place for us rock mechanics people.
On the capturing the gas instead of venting it or burning it, how expensive is it to do it? I mean, I understand the industry doesn't want to do it, but is it something that's completely out of the question, or is it something that just once we have regulations and then it'll do it and it would affect gas prices 2% or something?
I don't know. I don't know what the costs are.
I mean, it seems like
In principle, you could capture it.
In principle, it can be captured.
Yeah, in principle.
We have brilliant mechanical and civil engineers, and we can figure it out. The problem, but the point I made 2 points before. It's technology come lately. The industry has known about this problem for 150 years. Okay, as I said, countries have already banned flaring because of it's an abysmal thing to do, both for the landowner who is seeing his or her gas get burned and they're not getting paid for it, and it's bad for the environment. So why are we always waiting until the problem gets big before we solve the problem? Why aren't engineers CEOs?
Let me just interject a little bit. We didn't try to estimate how far down we could take that shale gas number because we saw no way to do that, although clearly, as Tony's saying, you could take it down. For these numbers, particularly for this one, that is what the General Accountability Office is telling us is the best available technology. So it's a lot better than there. And if you read that GAO report, they offer some fascinating differences across states. So that Utah has a lot better leakage rate than Colorado. Am I getting that right?
Colorado's better than Utah.
Yeah, Colorado's better than Utah because the state regulates it a lot more, and industry responds to it. It makes a difference. So regulation does matter.
But to be fair, all of the numbers below the first row are gas in general.
Absolutely.
Yeah,
There's
so I think we
unconventional,
really have to
conventional.
talk about gas versus shale gas too. Then it's really the top number is the one that Larry Brown's question got.
Absolutely.
That's right.
For that, there's nothing in New York that says when you're gathering lines or in New York, the industry has to go somewhere else without gathering lines in place before the well completes.
Oh, sure. No, I agree. It's a heck of a risk, especially without regulation.
Here, let me just amplify on that business because maybe people didn't hear it.
No question.
What's been going on in the Marcellus recently, as you probably know, is that companies have been trying to hold on to their leases by drilling before they're ready to produce. Only about half of all the gas wells in the Marcellus drilled in Pennsylvania are currently producing. The rest of them are shut in because the gathering line systems and the compressor stations haven't been built yet. So in the meantime, there's gas that could be going to market, and there's gas that's leaking that should be going into a pipeline. So again, it's a business influence on a technical problem.
Just a question about pipelines, and I was wondering if there was a consideration made with fugitive emissions that are traveling cross-country to the Northeast, which is a center for natural gas consumption, versus, locavore, I guess, gas traveling less distances, and if you did any, back the napkin calculations or what that might
No,
change.
I think that's a good point, and the answer is no. We developed, the gas pipeline storage and local distribution numbers, they say, in two ways. One, with these long-range transmission line data from the Russian scene, German scientists, and the other is by the Texas missing and unaccounted for gas. And those don't allow you to tease that apart. So there has to be some aspect of what you're saying, but it's not easy to put a number on it.
Oh, right.
We're going to take one or two more, and then we're going to let this break up just with this big crowd.
We'll hang around.
Yep.
Some people locally have become concerned about the LP gas and natural gas storage facilities and salt formations. Have you looked at methane leakage from like the NICEAG facility over on the other Seneca Lake? No, nothing like that.
I haven't seen any information on it either. There's really not. We have scoured. I mean, forget the peer-reviewed literature. That doesn't take long to scour. We've scoured the gray literature. Most of what, just give an aside, we posted some of our preliminary findings about a year ago online. Some was right, some was wrong. I got a huge email traffic, I'll tell you.
I'll bet.
And I've continued to get a huge amount of email traffic. But a lot of it came from industry insiders who said, you ought to look at this report, you ought to look at this. And we learned a tremendous amount of stuff we never would have found otherwise. So we have relied on people sending us stuff. Rene has scoured stuff. We've gone through all of the documentation that EPA has used in their new report. We've gone through all the documentation that the GAO has used. We've talked to a lot of people. I really don't think we're missing much, even in that gray literature report. And I'm not aware of anyone who's measured those sort of leakages from those sort of systems. Again, I think this is a right area that we at Cornell could do with appropriate scale micrometeorological techniques. I'm excited about doing that.
And again, my final comment, and I'll be quiet. So to Milt and Larry, I hope you don't gather from this presentation that we think we're right. There is no right or wrong. That's what we found. There's a challenge. Do the science.
Actually, in terms of you're missing the bigger, not putting in terms of electricity.
Well, I think it's in the report.
We do in our paper. I'll show
it's
it
in
to
the
you.
paper.
Could you give us a link?
I think you're being
The paper is not available until it's been published, which will be April 1 to 14.
That's pretty soon.
At that point, we will give a link through my website and elsewhere.
But we are going
It'll
to
be
post
freely
also
available.
these slides and further follow-up references.
We'll post these. We're not allowed to share the paper in the meanwhile.
So one other thing, the next talk that will occur in this room, I think, is by Rich Hout of the Houston Advanced Research Center. And I think a lot of the questions we can re-ask at this time, because their efforts are to look at control of flowback water and drilling associated emissions. So maybe about the technologies, maybe about what's better known. So come back on the 29th. Thank you all.